So this is a quote from Karl Popper. Science may be described as the art of systematic oversimplification, the art of discerning what we may with advantage omit. And that definitely occurs in Chem 1A. There are things that we can just leave out, and then we can understand the overall situation. So this chapter is Introduction to Solutions and Aqueous Reactions. I don't remember why I skipped the first section, but I think there was a good reason for it. I'm starting with 5.2. So, solution concentrations. Chemical reactions in which the reactants are dissolved in water are extremely common and very important. When we have a substance dissolved in water, something like salt in water, that forms a homogeneous mixture, that's called a solution. So a solution is a homogeneous mixture of two substances. Those can be two liquids, a solid and a liquid, a gas and a solid. You can have any combination of states. You can even have two solids making a solution. With metals, we call that an alloy. So brass is a solution. Stainless steel is a solution of different solids. A solution has two parts, the solvent and the solute, or solutes. So the solvent is generally the substance that there's more of, and the solute is what there's less of. And there can be more than one solute. You could have 5 or 100 solutes, but you can only have one solvent. These are mixtures, and so how much solute is in the solution is variable. It's not like a compound where the ratios are always fixed. The ratio is variable. Aqueous solutions are one where the water is the solvent, and that's what we mostly talk about. Now, the experiment we did on Tuesday, where we mixed zinc and iodine, and then we added methanol and heated it, that was a chemical reaction that occurred in methanol. So it wasn't an aqueous solution, but it was a reaction that occurred in a solution. So because the composition is variable, we need to be able to describe the composition. So we can use qualitative terms, dilute and concentrated, and these are just general terms. They don't have a number associated with them. And these words are used in the same way that they are in everyday life. So a dilute solution has a small amount of solute, and a concentrated solution has a large amount. Here we have an illustration. In the concentrated solution, if we zoomed in, we see there's a lot more solute particles in a given region than there is in the dilute solution. This makes me think of concentrated frozen orange juice, right? You buy orange juice at living here in the valley, why not just make your own? But you buy frozen orange juice concentrate, right? It's concentrated. Do you want to just thaw that out and drink it? Nah, too sweet. So what do we do with it? You put it in a pitcher and you add water to it. You dilute it. So you have made it less concentrated, more dilute, and now it's at a concentration that it tastes good. If you continue to add water to it, then it gets too dilute and it gets watery, and then it's not good anymore, right? So concentrated and dilute. Of course, we need quantitative descriptions of concentration. And so a common way that chemists use to indicate solution concentration is molarity. Molarity is a very, very important concept in chemistry. So molarity, it's abbreviated capital M. It's the amount of solute measured in moles, always in moles, divided by the volume of solution in liters. And so we can write it out as an equation like this. Molarity, abbreviated capital M, is amount of solute in moles divided by volume of solution in liters. So this is a ratio, a this per that, like density is grams per milliliter, but here we're measuring amount in moles instead of in grams. And we're measuring the solution in liters instead of milliliters or cubic centimeters. Yeah.
What is molality? I remember it's a thing, and I just don't want to get it mixed up.
Yeah, so molality is a thing. I think it's a stupid thing, but there is a reason for it. And we'll talk about it later. Molality is moles of solute per kilogram of solvent.
Oh, okay, so just instead of liters.
Instead of liters, and instead of liters of solution.
Oh.
Yeah. So this is for the volume of the solution. That includes the solvent and the solute. In molality, you measure the mass in kilograms of just the solvent. And there's specialized circumstances where molality is more useful. Yeah?
Why do we use moles instead of grams?
That's a good question. Why do we use moles instead of grams? Because when we do stoichiometry, we always end up with moles in the middle. And because chemists are looking at the reactions between individual molecules or between moles of molecules, we need to have a counting unit. It's more useful. We could measure, and we can measure and do measure concentrations as parts per million or grams per liter. There are lots of other measurements like that. But then if you're going to do stoichiometry, you have to get out the molar mass and convert the grams into moles. And so what I hope you'll see today is that molarity is really useful, because when we do solution stoichiometry, the molarity is given to us, and we don't have to calculate any molar masses. And that saves a lot of time. So it's also a little bit like molar mass, where you had a certain number of grams per mole. So this is a ratio thing, and it's not moles. So we see that capital M, that's a sad M, capital M, and I usually underline mine because, is that a lowercase m or a capital M? Lowercase? No, it isn't, it's capital. Whatever you said, I was going to make it be wrong. So I underline it because we should have big and small, but sometimes that's a little hard to tell. So I always underline my M's. But capital M means moles over liters. It's not the same as moles. Okay? In Chem 1B, after students have been successful in Chem 1A and they come to Chem 1B and we start doing stuff, and I realize that a bunch of them really have no clue what molarity is. And that's very tragic in my mind, because molarity is such an important part of chemistry. It is like density or molar mass in that it's an intensive property. It doesn't depend on how much solution you have, right? Because it's a ratio of solute to solution. And so the molarity doesn't change if you cut the sample in half. The molarity is the same. Whereas the number of moles would change, right? That's an extensive property. Okay, so here's an illustration of how you would make a solution with a particular concentration. Here we're making a 1 molar sodium chloride solution. So 1 molar is the way we would say 1 m, which is the same as 1 moles per liter. So a 1 molar sodium chloride solution, if we make 1 liter of it, then we need 1 mole of sodium chloride. So here we're using a 1 liter volumetric flask. This has a long skinny neck, and there's a line etched here. The skinny neck is so that when you add just a tiny bit of liquid, you see a difference in the level. And so you can get a much more precise measure of volume than if you were doing this in a beaker and trying to line up the level with a line on the beaker. You could add 5 drops of water and you wouldn't notice any difference, right? Here, if you add 1 drop of water, you're going to see a difference. So that's why it's got the long skinny neck. So for 1 liter, we need 1 mole of sodium chloride. So we use the molar mass to find out we need 58.44 grams of sodium chloride. We weigh that out in the balance, and then we add it to the flask. Next week we're going to do an experiment where we make a sodium chloride solution. And so you're going to be doing something very similar to this. Getting the solid into this flask can be a little tricky because you want to get all of it in there, and you've got this really narrow neck, and so it can be a little tricky. A funnel can be very, very helpful. Then we add some water, and we get the solid to dissolve. We don't want to fill it up to the line right away, because once the level of liquid gets up into this neck, it's really hard to mix. The only way you can mix it is to turn it upside down and wait for the air bubble to go up and turn it over again. So we add some water until we've got a good amount in here, and then you can swirl it and shake it and get it to dissolve much more quickly. Once you've got the solid dissolved, then you top it off, you fill it up to the line. Then you need to cover the top somehow. This one looks like it would have one of those plastic lids. The ones we have ground glass stoppers. You put a stopper in there, you hold onto the stopper, and then you need to mix it thoroughly, which means inverting it usually 10 to 20 times. You really can't overdo that. You need to get it mixed up. And so then you have a solution that has 1 mole of sodium chloride per liter of solution. So now, instead of having to use the balance, if we needed half a mole of sodium chloride, I don't have to use a balance and measure out half of this. I can measure this with a graduated cylinder. I would need 500 milliliters or half a liter if I wanted half of a mole. And that's much easier. Yes?
So it's important to dissolve it because we want to be able just to take from the solution at the end.
It's important to dissolve it for a couple of reasons. The most obvious is that it's hard to mix it after you get it to the volume, and it's going to require a lot more mixing until the solid dissolves. The other thing is that as the solid dissolves, the volume can change. So if you think about it, if you had a glass of water at home, you filled it to the very, very top, and you took a teaspoon of salt and poured it in there, what would happen? Would some water dribble over the edges? Yeah, because the salt takes up some space. But the salt takes up a different amount of space before and after it's dissolved. And so as the salt, salt here in this example, as the salt dissolves, the volume of the solution can change slightly. And so we want to avoid any mistakes caused by that. Some things take up more space, some things take up less space, and there's no good way to predict what's going to happen. Yeah?
Why is that? Like, shouldn't a chunk of salt take up the same amount of space as like the equivalent mass of smaller pieces of that salt?
You would think so. The thing is that when the sodium chloride dissolves, we no longer have that same structure of sodium and chloride ions interacting with each other. The ions are separated. And so the way the ions are in the sodium chloride may be more or less dense than when they're separated and surrounded by water molecules.
So just to clarify, when you say dissolve, you don't mean like breaking the small bits, you mean separating into the ions?
Separating into individual ions.
Okay.
Yeah. Yeah, it's not just that we've got smaller chunks of solid. It's that it's separated into individual ions, which are on the same scale in size as the water molecules, and so they mix thoroughly, which is different than a suspension or a colloid where you have small particles that may stay in solution, they may stay up there, but they are larger than the water, and they're large enough actually to refract and deflect light, and so that's what makes it cloudy. Yeah.
So if you wanted to recover a certain amount of a solid from a solution, is it common to take a known molarity solution and then isolate the solid by boiling off the water or whatever?
You could do it that way, yes. Yeah. So if you had, this 1 molar sodium chloride solution available and you wanted to get a certain mass of salt, you could calculate the volume that you need, and then you could heat it and evaporate the water off. since most of these reactions occur in solution, we don't actually end up needing to do that. We want it in solution, and we're going to mix it with another aqueous solution. And so we're just concerned with the amount of solute that's present. So how many moles of solute are required to make 3 liters of a 2-molar solution? So this is a conceptual problem, so we shouldn't really need a calculator here. So if I have 1 liter of this solution, and this 2 is 2 moles per liter, how many moles do I need in 1 liter? 2. So I need 2 moles in 1 liter. If I had 2 liters, I'd need 4, and if I have 3 liters, I need 6. That make sense? You guys seem a little stunned.
It's because the way you explain it.
Did I explain it badly?
Because I think most of us, when we came up with answer 6, thought like math, we put 2 molarity equals.
And that's actually better.
Yeah, it's easier,
right? So if I have 3 liters, I can use this molarity as a conversion factor. The units cancel out, and I get 6 moles. And I think that is a better way to think about it. I'm trying, although maybe it doesn't help, I'm trying to be more conceptual to make sure that we understand the idea behind this, that in each liter I've got 2 moles, and so if I have 3 of them, I need 3 times 2. Anybody have any questions? Because people think about the world in different ways, which is good, because if we all thought the same way, we wouldn't get much done. So calculating solution concentration. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So it says calculate the molarity. So molarity, I need to know what that means. Molarity is moles per liter. So I need the moles of solute and I need the liters of solution. Was I given either of those? They gave me the volume of solution, right? So the solution volume is 2.50 liters. They didn't give me the moles of solute though. They gave me the mass. Can I take the grams and convert to moles? Sure I can.
So
Mm-hmm.
when we're looking at this, it does not matter for us. It doesn't matter what it's breaking down into for us to understand how many
Moles per liter is
Correct.
the original solution that we're like, it's this many moles.
Yeah, we'll talk about that later. When sodium nitrate, which is an ionic compound, dissolves in water, it separates into ions. And so there are times when we're interested in, well, how many moles of sodium ions are there? How many moles of nitrate ions are there? How many total moles of ions are there? There would be twice as many moles of ions as there were moles of formula units. And sometimes those things matter. Most of the time, we're just interested in moles of the formula unit, formula, or molecule unit for a molecular compound. So I'm going to convert grams to moles. So I have 45.4 grams of sodium nitrate. And I want to convert to moles. and divide by grams. So I need the molar mass. So in the periodic table, I find sodium is 22.99 and nitrogen is 14.01, and then I've got 3 oxygens. And it tells me 85 when you go to the grocery store, and it comes out to be exactly $100. You're like, do I get a prize or something for that? Is this an exact number then? It looks like it, right? It's a whole number, right? All whole numbers are exact. No, it's not. This is the calculator not understanding significant figures. All of the numbers I used to calculate this had 4 significant figures. They all had 2 decimal places. No matter how I do it, I should end up with 4 significant figures and 2 decimal places, right? So how do I do that with 85.00? So I need to add 0.00 to remind myself that this has 4 significant figures. So 1 mole is 85.00 grams. So 45.4 divided by 85. My original mass had 3 significant figures, so the result of this is going to have 3 significant figures, but I'm going to write down 2 extra digits to avoid rounding errors. And I underline that 3rd digit to help myself remember 3 sig figs. So that's the moles, and so that's what goes up here. So I can't even copy things correctly. And then I just divide. I take that number of moles and divide by 2.5. The units just sit there, moles per liter. 3 sig figs, 3 sig figs, 3 sig figs. And then I'm going to round it. And so this is 0.214 moles per liter. Or I can call that 0.214 capital M.
Do you usually write like the solution of the water afterwards, or you don't usually label it like grams oxygen, or you don't put moles sodium water?
That's a good question. Do I need to specify moles of what? Or liters of what? I'm dealing with molarity, and when we talk about molality and about percent concentration, I will try to trick you. But when we're dealing with molarity, if I would try to trick you and say that it's 2.5 liters of water, there's no way for you to know what the total volume is, and so we don't do that. I don't know how much water is in here. I only care about the final volume. And you can see when we made the solution with the sodium chloride, I put the sodium chloride in there, and I'm adding water and mixing, and I'm adding until I get to a certain volume. I don't know the amount of water that I put in there, and I don't care. I only care about the volume of the solution. And here we have no chemical reaction going on. We're just talking about this one thing. And so it's always fine to label moles of sodium nitrate. That's always fine. This is a situation where we can get away with leaving it off. Anybody else have any questions? .214 capital M. So molarity is a very, very useful conversion factor. And here we go with the dimensional analysis again. So we can use molarity to convert from liters of solution to moles of solute, or to convert from moles of solute to liters of solution. Because when we see this 0.5 capital M, that means we have 0.5 moles of solute for every liter of solution, and so it's best to write it this way with moles per liter instead of using the capital M, because the capital M disguises the fact that this is a fraction. So how many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? Some problems, like calculating the molarity, we needed to use an equation. A lot of these end up being dimensional analysis. So if you're not sure what to do, I'd say try dimensional analysis first, and then you might find out you need an equation, but no harm done. So I read the question. I'm going to pull the numbers out and write them down, because I'm not exactly sure what I should be doing here. So I have 1.55 liters, and they're telling me 0.758 capital M. Capital M is more convenient to type, but that's moles per liter. And if it's helpful to you, specify this is liters of solution, this is liters of solution, and this is moles of sucrose. We gave you the formula. So those are the numbers I'm given. As I'm looking at this, I'm thinking, that looks like a conversion factor. Anytime you get the per moles per liter, that's probably a conversion factor. This 1.55 liters is just going to sit there. I can't use that to do anything, right? So I've looked at what I'm starting with, and then I'm going to look at what am I supposed to find? Grams of sucrose. Right? So grams of sucrose. Now I need to figure out how to get from liters of solution to grams of sucrose. Sometimes it's one step, sometimes it's 2 or 3 steps. And that's where making dominoes with the units on there can help you. And so if you're at all iffy on unit analysis, ask me to show you how to play dominoes with this. Because once you see how the pieces go together, then you don't need the index cards anymore. You can do it in your head. But you have to be able to see how the pieces go together. And I think the dominoes can really help with that. So I'm trying to go from liters to grams. I've got this that was given to me. I'm probably going to need to use that. And when we're missing a unit in the middle, what do we try first? Moles in the middle, right? So I'm probably going to want to go to moles. So I can go from liters of solution to moles of sucrose. And the conversion factor here is the molarity that was given to me. Then can I go from moles of sucrose to grams of sucrose? Sure, I just use the molar mass to do that. So finding the path is the important thing, and on that extra credit worksheet, I'm going to make you literally write the path out for every single problem. Even if it feels stupid, you want the extra credit, you have to humor me and write out the path. It really, really does help. Okay, so I've got liters to moles to grams. That tells me what goes in my equation. 1.55 liters to moles to grams. I think most of you, once you've got this, can translate that into this equation down here. It's coming up with this that's the hard part. So I put this unit over here because I'm going to cancel those out. And this unit down there, cancel those out. All the units in place, they tell me where to put the numbers, so I don't have to remember, should I multiply or divide by the molar mass? I don't even need to think about it. I'm just going to look at where are the units. The molar mass goes with gram, so I'm going to multiply. And here, moles per liter, I don't have to think, should I multiply by the molarity or divide? I'm just going to put the number where the units tell me. So this number, 0.758 moles for every 1 liter of solution. I don't know how I did that. 0.758 moles per 1 liter of solution. And then I need the molar mass, so this is something I'm going to have to calculate. 12 times the mass of carbon, 22 times the mass of hydrogen, 11 times the mass of oxygen, the calculator's giving me 342.296. Yeah, I would have 4 sig figs. Those extra 2 are fine. And that's grams for 1 mole. Each of these has 4 sig figs. So the molar mass is 4 sig figs, but the answer has 3 sig figs. Because I started with 1.55 and my molarity has 3, but this has more, which is good because then we just don't even have to think about it. So 1.55 times 0.758 times 342.296. 402.16 grams, 402 grams. That's a good question. Does it matter if I put a decimal point here or not? It does not, because the last digit isn't a 0. If this was 400 and I wanted it to have 3 significant figures, I could indicate that with a decimal point, but scientific notation would be better. Any other questions? This is a really, really important kind of calculation for chemistry. .402 grams. This is another conceptual connection. So conceptual means we shouldn't really need a calculator here. So we should try not to overthink it. If we dissolve 25 grams of salt in 251 grams of water, what's the mass of the resulting solution? Just the sum, right? Conservation of mass. If I put 25 grams of something in a container, and then I put 251 grams of something in that same container, the masses add. Can I predict what the volume is? No, can't. Because I don't know how the salt and the water are going to fit together, but I can predict the mass. Any questions? Sometimes a question like this on an exam, a lot of people will get wrong because we were doing all these things with molar masses and stuff, and so then you try to do that with this and calculate the molarity or something. And that's not what the question's asking. It's just, what's the mass? So just like with frozen concentrated orange juice, we often store chemical solutions in a more concentrated form than we are going to use them in, because it takes up less space, and then we can make lots of different concentrations from them. These are called stock solutions. We keep them in stock and we store them in the stock room. They're stock solutions. So when we want to make a new solution from this, it has to be a solution of lower concentration. What we're going to do is we're going to take, just like with the orange juice, we're going to take some of the stock solution and then we're going to add more solvent. It's almost always water. So when you make the frozen orange juice into drinkable orange juice. There's a certain amount of orange goodness in that little can, right? And you pour it into the pitcher, and then you add usually 3 cans of water. Do you have a different amount of orange goodness in the pitcher? No, it's the same amount of stuff. It's all still there. The difference is you added water, the volume is bigger, but the orange stuff is the same amount of orange stuff, right? When we dilute a chemical solution, the moles of solute stay the same. We're changing the volume, the concentration changes, but the moles of solute stay the same because we're not taking any solute out, we're not adding any solute, all we're doing is adding solvent. So this is the equation we use to do dilution calculations. M1V1 equals M2V2. Students usually like this equation. If we look at the units here, M1V1. So that's moles of solution 1, or that's moles of solute per liter. Stop. That's moles per liter times the volume, and the volume cancels out, and that gives us moles of solution. Moles of solute, sorry. And over here, M2V2, that's moles per liter times liter. Those liters cancel out. This is also moles. So the moles in each solution are the same. What's changing is the volume. If that seems like voodoo or something, you can use the equation successfully without really grasping that. So don't worry about it. So this is how you might dilute a solution. And here we're not specifically doing the calculation, but we're just looking at how the calculation works. So we're making 3 liters of 0.5 molar solution from a 10 molar stock solution. So here we're measuring out 0.15 liters of 10 molar stock solution. So 10 molar is 10 moles per liter times 0.150 liters. That gives me 1.50 moles. Yes? So I'm going to put that in a flask. This is a 3-liter flask. And I'm going to add water. And now I've got 3 liters of solution. And the molarity is 0.5 moles per liter times 3 liters also equals 1.5 moles. So that's how the equation works. The amount of moles is staying the same. The concentration gets smaller, the volume gets bigger. To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? We have the word dilute. I find that students want to use the dilution equation in other places where they should not. It can only be used for dilution. So when can you use it? Well, if you see the word dilute, you can use it. Another clue here is the title of the example, right? So what I'm going to do is I read the problem, I'm going to pull the numbers out, and then we're going to identify what they are. So I have 100 milliliters, and I have 5.00 molar, so that's moles per liter, and I have 0.750 moles per liter. So diluting, I'm going to use the dilution equation. Molarity 1 times volume 1 equals molarity 2 times volume 2. So I need to identify what these pieces are. It doesn't matter, I've got two solutions. It doesn't matter which one I call 1 and which one I call 2, as long as I pair the volumes and the concentrations up correctly. You see that these two go together? 100 milliliters of 5 molar. Those are paired. That's what I came to first. I'm going to call those 1. So this is a volume. That's volume 1. This is the molarity that goes with it. That's molarity 2. No, that's molarity 1. Okay? And then the other molarity must be the other one, molarity 2. So we identify what the pieces are. And the question is asking for a volume. So I'm looking at my pieces here, and I have 3 of the 4 variables in the equation. I'm missing 1, so I can solve the equation for the one missing thing. I need to rearrange the equation. So here's a little bit of algebra. I want this to say volume equals. I want volume 2 to be all by itself. So I need to get rid of the other thing on that side of the equation. If I divide M2 by M2, it cancels out. In order for this to still be equal on each side, I have to do the same thing to the other side. If you're a little sketchy on rearranging equations, please ask me for help. So I've rearranged that, and that's showing me volume 2 is equal to molarity 1 times volume 1 divided by molarity 2. So I'm going to plug my numbers in with their units. So molarity 1 is 5.00 moles per liter. And volume 1 is 100 milliliters. And then molarity 2 is 0.750 moles per liter. So before we do any unit conversions, let's see what happens with the units. There's some units that cancel out, right? I've got moles per liter in the numerator and moles per liter in the denominator. Those are going to cancel each other out. That leaves me with milliliters, and what's the unit that I want? Milliliters. It specifies that we need to give the volume in milliliters. Sometimes you would need to convert that into liters, but this time I don't. So I can just do the math. 5 times 100 divided by 0.75. So volume 2 equals 666.6 repeating milliliters. How many sig figs? 3. So this is going to round to 667. Phew, that was almost a scary number. Milliliters. Does it make sense? So if I take 100 milliliters of this concentrated solution, I'm going to dilute it. I'm going to add water. So this should be bigger, right? If your diluted volume is smaller, it's like you put the orange juice in the pitcher and you add water and it shrinks. No, that's wrong, right? So that would mean you've got something backwards or upside down in your calculation. So it's a clue to look at your math. Any questions? 667 milliliters.